In this problem, we're going to show that a function is uniformly continuous on the whole line, and this function is complex enough that we're going to have to use 5 or 6 different steps to do it. And if you're a student in real analysis, I think this is a really good problem to focus on the concepts. So uniform continuity, just to review the definition, it's basically saying in what looks like a complicated way that no matter how close we want our outputs to be, if we want our outputs to be within epsilon of each other, that there is a uniform way that we can choose a distance between our inputs so that if our inputs are within that distance delta, then our outputs will be within that distance epsilon. Now I'm assuming in this video that you have learned the definition of continuity and uniform continuity. I can make other videos going through the intuition behind this and have some really cool animations using Desmos. But for this video, we're going to go through how you could build everything up to get this result. And the way that we're going to start is we're going to start by saying, well, first of all, it's going to be helpful to know that our function is just regular continuous. Now, regular continuous on R is a little bit of a different statement. It actually will take these same quantifiers, but it will put them in a different order. And so it will say for any point in your domain, there is some delta that will work for that particular point. And so we're going to just take this whole little section up here, and we're going to put that down there. Now, I know these look really similar, but what's important here is that when we're talking about a function we say it's continuous, the delta that we supply is allowed to depend on everything that comes before it. So that delta might depend on epsilon, probably will. That delta might depend on the point that we chose. So with uniform continuity, we have to define delta a little bit earlier. And so the delta in uniform continuity can only depend on that epsilon. And so we're going to get to this. By the end of the proof, you'll kind of see how we can put everything together. Now, at this point in the class, you probably would have proven a bunch of theorems about the continuity of basic functions. And so if our input, the point we're measuring continuity at, is non-zero, well, our function is a composition. Really, it's a product of x with the function sine of 1 over x. And that's a composition of continuous functions, because all of these functions, rational functions, polynomials, trig functions, are all continuous at points of their domain. And so kind of basic continuity is giving you that we get continuity of our function f at all non-zero points. And at 0, we have to be a little bit careful, because 1 over x is not defined at 0. We can't appeal to that sort of thing. And so the cleanest way I know to do this would actually be to write an epsilon delta proof, checking continuity manually at the point 0. I can make another video about that if you'd like to see it. Just leave me a comment. But I just want to talk about the flow of this whole proof here. And so in this step, which would take a bit of writing actually, we can establish that the function is going to be continuous on our real line. Now, just because a function is continuous on the real numbers does not mean that it's uniformly continuous. And in fact, you have to look no further than the function y equals x squared. Right? The parabola given by x squared is indeed continuous on all of the real line, but it's not uniformly continuous, because as the graph gets steeper and steeper, it will be harder and harder to find a delta that works in that area. Right? You're going to have to get points closer and closer together to account for that steepening part of the graph. And so although we can find a delta that would work at any point, we're not going to be able to find a consistent delta that would work in general, because the graph is getting kind of arbitrarily steep. And so you might wonder, well, maybe the same thing happens with our problem. Indeed, the graph does get arbitrarily steep right in the middle. that might be cause for concern, but we also notice something a little bit happier, is that as we go further and further away from the origin, our graph actually gets flatter and flatter. And so our function is going to have pretty controlled slope out there. And we're going to see that this is the magic that we need to finish this proof. So we're going to focus here on the middle. And so if you want to just focus on that, that would be fine. I actually start by focusing on the closed interval from -1 to 1, because there is a beautiful theorem that you would prove in a real analysis class that any continuous function is going to be uniformly continuous on a closed bounded interval. So I collected a bunch of theorems up here that you might want to use in a class. This is, I think, the most important one, because studying functions on closed bounded intervals like -1 to 1 is something that happens all the time. And so from that theorem, which is itself a lot to prove, we know that no matter what epsilon we pick, there is going to be a delta that works for any points that we choose inside of this interval here. Okay? So we're on our way towards solving this problem. So now what we're going to do is we're going to kind of shift perspectives a little bit, and we're going to look at some infinite intervals starting at 1/2 and going off to the right, and the analogous picture to the left. And if we look at our function, well, out there our function is just x times sine of 1 over x. And as we notice, the slope seems to be kind of tapering off. In fact, the steepest part of the graph seems to be right at the beginning. Right? And so whatever the slope is at that point, it seems like it's only going to get smaller and smaller. And in fact, you can do a calculation, just taking derivatives and using properties of sine and cosine. You're going to be able to show that the slope of this graph is going to be bounded. And that is actually theorem 5 in our list. And so if you have a function that's differentiable and the derivative is bounded, then our function is going to be uniformly continuous. Now this works even on infinite intervals. And so what we're saying is that no matter what epsilon you chose, there is going to be a delta that works on the entire infinite interval for the green on the right and also the green on the left. So now what we've done by using these two powerful theorems, which I'll indicate, I guess, with number 1 and number 5, now we can put everything together. And this is where, like, I love analysis because it really feels like you're building something, like you're doing construction. Because now what we can do, we can say, well, you know, I know that there's a delta that works on the closed interval from -1 to 1. By the way, when I say something works, I just mean this long statement that I don't think we need to rewrite every time. And so there's going to be some delta that works on the interval from -1 to 1. There's going to be some probably different delta that works on those infinite green intervals starting at 1/2 and -1/2. And then I'm going to say, well, if that was how close you needed to be for things to work separately on all those things, let's take the smallest of those three numbers. That's only going to make things closer together. And then I claim that that's going to work everywhere. And the only reason, you may notice I've got this 1/2 written in there. That's just because if we look at how our intervals overlap, there's a chance that, like, the domain of our restrictions of our functions, it might cause some troubles. And even if it doesn't, it doesn't hurt to kind of add that restriction in there, to just say, hey, we're going to make sure that our delta is small enough that we don't kind of pop out of one interval versus the other. And this is our proof. And so by putting everything together, we had to use derivatives, we had to use epsilon delta, we had to use products and compositions, we had to kind of cite large theorems, and then we had to put things together in a way that goes back full circle to the original definition. So I love this problem. I'm happy to post follow-up videos. Thank you for watching. If you like this, please like and follow and subscribe. I really appreciate it. Have a great day.